Let us today continue this chapter on computer aided design for printed wiring boards. Alongside, we are also looking at the subtopic called design for manufacturability, and I would also probably introduce a few aspects on design for reliability at the end of this particular chapter. So, in the earlier class we had introduced to the basics of CAD, the need for CAD, and CAD for printed wiring boards essentially means that you are taking a major step forward in designing system level printed wiring boards, in defining system level package substrates, because as you know, the printed wiring boards, as you call it, act as system level substrates. Much more functionalities are built into the organic or the ceramic substrate, as the case may be, depending on the application, and therefore, you need not look at printed wiring boards as just a simple means to house your components and simple interconnections between components. It is much more than that, because today CAD not only defines the size of the product, the size of the printed wiring board in some sense, as we saw in the last class, defines the size of the product, the density of the product. CAD also plays a major role in package electrical design and package thermal design. So, once you do the basic interconnections of components, you are going to do a lot of simulation, both electrical and thermal, to make the product more reliable. That is why I said towards the end of this chapter, we will also discuss some key points on design for reliability. So, if we can proceed, continuing from the last class, we defined in the last class three major points as to the selection of the components and the need for CAD. Today, if you look at electrical circuits, they are made by interconnecting discrete passive and active components on a suitable substrate. In the last class, I mentioned that it is the designer's choice, it is the designer's prerogative to select a suitable substrate for a particular defined application. Now, once the substrate is selected, you are basically going to add or mount various active devices and passive devices, and then build a circuit along that. Now, the density of this particular activity can be low, medium or very high. So, that depends on the number of interconnections, the number of components. That is why we use the term component density and board density. Now, what are the basic active devices that we can think about? Basically, they are the integrated circuits, individual ICs, microprocessors, microcontrollers, various transistors and so on. We can also have on the board mounted single chip modules, like your BGA is a single chip module, your CSP is a single chip module, and a PGA like your Intel processors or the AMD processors are single chip modules which will be mounted on the printed wiring board. You can also have multi chip modules connected, then various transistors, diodes, etc. So, these are the basic active devices that could be used. In the case of discrete passives, you will be using resistors, various forms, various types, various values, capacitors of various values and sizes and different types, because you can have resistors and capacitors in a through hole format or in a surface mount device technology format. Then variable resistors, potentiometers, trimmers, inductors, inductor coils, connectors. There are various types of connectors available in the market today, and the connectors are very essential if you are integrating 2 or more boards in a particular large system. Also, you will be using various mechanical and electromechanical components like relay, transformers, display devices, liquid crystal display, other forms of display, and so on. So, how are you going to tackle the entire scenario given here? If you have a high density board, obviously you will have different types of these components that need to be interconnected on a single substrate platform, and how well you can utilize your CAD system to its complete advantage or complete utility value, and then make a very good design out of it, and whose output can easily get integrated with your electrical simulation or thermal simulation. Now, these connectors, very often we do not give due importance to the connectors. We normally give importance to the active devices, but connectors, let us say, for one printed circuit board to another printed circuit board, play a very significant role. So, if you can look, if the camera can focus on this board here, now you can see there is a connector here, there is a connector, and there are different types of connectors. This is also known as a connector. This is a edge connector, and you can also have different types of other connectors. Now, these will get integrated with other boards. For example, this could be a daughter card that can go to a motherboard. Therefore, there should be a reliable connection between the 2 printed circuit boards. So, connectors play a very significant role. Probably they are the weakest link on the board, and therefore, it requires a lot of care in selecting what type of connectors you require for that particular application. The connector types are power connectors, signal connectors, and simple PCB to PCB connectors. Now, if you look at a power connector, because of power handling requirements, large power, you may have to choose very carefully the connector type. The size may be different. Signal connectors, on the other hand, can be very small in size because of the current carrying capacity and the power handling being different from the power connectors. PCB connectors essentially could require to be used for connecting 2 modules. Okay. On a let us say a server, you may have 16 different boards connected to a major platform, a major board, and individually you can pull out these printed circuit boards and attach to the motherboard by means of simple connectors. But these connectors have to be reliable. Therefore, the selection is based on the number of required contacts, number of pins that is required for this connector contacts. Then what is the operating voltage and current. So, accordingly, as I said earlier, in the classification of connectors, you will have to choose based on the operating current and voltage requirement, because the type of finish that is provided on the connectors will be different for each of these classified connectors. What is the voltage drop permitted? Does the material that is used in this connector allow that? How often you are going to make and break the connection using these connectors? In some cases, you will be pulling out these PCBs onto the motherboard back and forth a large number of times. Therefore, these small pins have to be very sturdy. The plating on these connectors have to be essentially gold finishes because of the contact pressure that is used. Therefore, you look for the contact resistance that is required, and therefore, you will choose connectors based on the plating finish. Typically, you can have a tin plating finish, you can have gold plating finish. Earlier, we were also using tin lead plating finishes. and other things like alloy 42 and so on. So, obviously, there will be a wide choice. You have to choose the connector based on the space limitations, the number of times you are going to make and break a circuit using these connectors. Now, the CAD emphasis, the approach to CAD for a designer is that the effects of a CAD layout on the final product quality and the cost of manufacturing has to be definitely considered, because otherwise the utilizing the entire power of a CAD tool is lost. So, you have to really dig into the CAD software tool and look at how well you can utilize to get a final product that is of high quality, and at the same time you have done an entire process sequence using CAD where it is manufacturable first of all, and it lowers the cost of manufacturing. A designer should have a general understanding of the end user's assembling capability. So, we talk about manufacturing first, then we also talk about assembly. So, a designer should be able to quickly recognize the loopholes in manufacturing, the prerequisites for a particular application in manufacturing, the key issues in assembly, and what failures can happen if you do not take care of each of these two very important aspects. Overall view of the manufacturer's capability should be understood, because today the board fabrication is a very complex process. We have various technologies available today in PCB manufacturing. Therefore, there are many companies which give various technologies, various chemistries that have been researched for a long time and that have been bought with a large capital investment, and therefore, if the manufacturer wants to deliver a high quality printed circuit board, he also needs to interact with the designer and provide these advanced facilities to the designer, so that the entire combination of providing a high density, high reliability board can be fruitful. Reasonable understanding of processes like high density interconnect, because today, as I have been mentioning when we talked about packages, high density interconnects are the order of the day. Even if you want to make a BGA substrate, you have to go in for a high density interconnect, multi-layer. Then obviously, a designer should be aware of the design rules and manufacturing processes that are closely related. Now, the first thing in a CAD process is that there will be a paper diagram. For example, assume this is a paper diagram that you have of a schematic circuit of an electronic circuit. You have to now do a schematic capture using your CAD tool. What do you do for that? You have to create a circuit diagram using a basic graphics program that will be available in the CAD tool. Now, you generate circuit symbols on the screen, like you have a symbol for a IC, NAND gate, AND gate and OR gate and so on. So, accordingly, you go to the library of the CAD program, generate the circuit symbols or pick the circuit symbols that is available in the inbuilt library of the CAD software. If it is not available, then you have to generate by yourself based on the data sheets that are available. You generate the circuit symbols on the screen. So, schematic capture is all about symbols, very important. Okay. Now, you generate interconnections once you have inputted all the components that are required for that particular design circuit. So, now you generate interconnections and verify. So, these interconnections are basically copper wires that you are going to realize to connect component to component. We will detail all of these aspects shortly. Now, after that, at this stage, once your schematic capture is done, you can take a printout. So, you can take a printer output, you can take a plotter output. Obviously, today nobody uses a pen plotter, but you can take a printer output for further study. The next step will be from this schematic capture to generate what is known as a netlist. Netlist generation is a universal task, whatever be the CAD software that you are going to use. You have to generate a netlist based on your schematic capture, and this netlist will be the first source input for all other modules in any CADware. Okay. So, it could be in various formats, but it is easily editable using your WordPad or Note or any other word processing tool. You can read the netlist and understand how a netlist is generated. As the name indicates, it is a collection of various nets or interconnects that you have generated. To do a schematic capture, the first requirement is make sure you have a very good symbol library, and afterwards you have a parts library that you need to annotate or relate to the symbols that you have picked for that particular design. So, basically, if you are in an organization or if you are in an institution where a lot of designs are being done, you have to spend a lot on looking at a CADware that provides very good library manager and which can be editable, that can be utilized for your future different component symbols that may not be available online. Okay. So, make sure that when you buy a software, you have a very good library. This is a must, because you are paying large amount of money for this particular source of information where you can pick these symbols and start working with your design. Some CAD software will have circuit simulators, low end software will not have simulators, but you can work with low end software and utilize those schematic and netlist information to input to another high end software which will have a simulator. Okay. So, in case your CAD program or your EDA tool, electronic design automation tool, electronics design automation, that is the term used for CAD programs which contain all the aspects of printed circuit board design. A circuit simulator will have simulation for circuits for determining the electrical performance. You can do a digital circuit simulation, logic verification and fault simulation. You can do timing analysis of a particular net, glitches in the net and their effects. You can minimize these parasitics. Analog and power circuit simulation, because for power circuits you may have different requirements that you need to meet, and therefore, carefully you have to simulate. Then power dissipation analysis, again as you have seen from the definition of packaging, power dissipation and power delivery are important terms that need to be looked into by a packaging engineer. Then the next module in any CADware will be PCB layout design, which means here you are working with component placement. So, in a given area which you determine as the PCB size, you have to place the entire set of components, both the actives, the passives, the electromechanical components and other parts into that given space. So, the real estate here is expensive. So, you have to make sure you utilize the CAD program to make a very good layout. The orientation of the components also is a key factor in deciding or achieving high density. For example, if you have two integrated circuits, you need to align them in the same orientation instead of having one like this and one in this direction. So, a combination like this is good, whereas a combination like this is not accepted. because there are various reasons for this. Not only just from the aesthetics point of view, it occupies more area, it provides difficulty in routing your traces, it provides difficulty during assembly of these components. Okay. So, the layout module will also contain various aspects in placement, then comes routing, that is manual and auto routing of the interconnects that you have specified in the schematic capture. Then you can do a design rule check or a design rule verification, basically to look at current density, the line widths that you require for manufacturing, line spacing that is specified by the manufacturer, clearances and so on. And your layout should also be able to generate multi-layer boards, right from 4 layers to, let us say today even 64 layer boards have been successfully fabricated. But obviously, in a commercial board or in a handheld device or a communication product or a desktop motherboard, you will not require this many layers. Typically, the handling capacity will be around 4 to 12 layers. Higher layer count is usually for more strategic applications. So, multi-layer capability should be possible using your layout. We will also talk about various other parameters that I mentioned here, like the clearances that are required at a later point of time. Now, the output of this activity that we have seen so far, the activity that I have listed so far, right from schematic to simulation to the layout design tool, will be to create outputs for drilling, because as you know, if you look at this board here, there are a number of holes which will interconnect components. Even in the case of this particular board here, there are various through hole components, because on the back side also you see assembly being done. Therefore, if it is a 2-layer board and if you have to interconnect these 2 layers, you have to create a mechanical hole, and this mechanical hole has to be made conductive. So, drilling becomes a very important step, a very essential activity for multi-layer fabrication of your designs, and the input from your CAD based on the layout that you have done will be utilized for drilling using a numerically controlled drilling machine. Then the another output that can be generated from your CAD program is to generate a solder mask pattern for both sides. I will explain briefly what is a solder mask. We will talk much about solder mask later. Visually, as you can see in this picture, the green areas are the solder mask material. Solder mask is nothing but an epoxy paste that is being used here. What is the function of this solder mask? If you look at this particular board, all the pad areas are open. You can see the gold color areas, these are the pad areas which are open on both sides, and other areas which do not have the component pad mounting, okay, are covered with a green paste material called the solder mask. Now, it is not easy to apply solder mask in the non-circuit areas without utilizing the layout assembly details. That is why we generate a solder mask pattern for both the sides of a double sided board. So, you will use photo imaging techniques to make sure that your pads are open, the holes are open, and all non-circuit areas are closed. What does it do? The solder mask here, it is an epoxy, therefore, it is a dielectric material, right. So, what is the function of a dielectric material? It protects all your conductor areas, it takes care of bridging of any pad or let us say your tracks, and it takes care of providing better electrical performance like elimination of crosstalk, noise and so on between two close conductors. So, if you imagine two conductors here, then imagine there is solder mask in between these conductors and the outside areas. Obviously, it provides a better electrical performance. And imagine in a high density circuit, these lines will be very close, and also the pads will be very close to each other. A pad will be very close to a via structure and so on. The other thing that you will have to generate, or it is possible to generate using a CAD, is legend printing masks. If you look at a normal finished PCB like this, close to the assembly, the component marks, you will see white numberings being done that denotes the name of the component, the reference designation of the component and so on. This is the final finish that is done on top of the solder mask. This is done in white ink. Now, this is done by screen printing process. Therefore, for this also you have to generate a mask. You have to generate a mask for a solder mask, and for CAD you can directly send the file to the manufacturer to drill the number of holes that is required. So, a drilling file will essentially contain information like number of holes to be drilled in a particular size of a PCB, the different dimensions of the drill bits that is needed to be used for that particular design, and for each of those sizes. For example, if you take 0.6 mm drill, there may be 160 holes. Then if you take 0.8 mm, there may be 30 holes. So, this kind of a list is generated by your CNC drill output, and it also gives the XY coordinates of the places where the drilling has to take place, including the mounting holes. What is a mounting hole? You see here in this particular PCB, again at the edges you will see holes that are used for mounting, large holes even in the center of the PCB in some cases. These are mounting holes that are used. It is not providing any electrical connection. It is a mounting hole that is used for using the PCB to be fixed onto a chassis of a product. The next one is you can also generate outputs for bare board testing. Obviously, when a board is finished, you have to test the board for shorts and opens. A short is an electrical short and open is a electrical open, no connection. So, during the process there could be reliability issues. So, at the end of the process sequence, your CAD netlist can be used for automated test equipment input to do a bare board testing. Basically, this is a electrical test, which is very essential, which is compulsorily to be done by any manufacturer today. You can also generate masks for all the electrical layers for a multi-layer board. If you have 32 layers to be done, then you have to generate 32 masks. If you want to build a 2-layer board, you build a 2 masks. Now, it is time for me to show you what a mask is. If you look at this capture here, what I am showing is a plastic sheet. This is a polyolefin layer, and you can see here plots of the pads of the components and the traces. Okay. So, this is the mask for one single layer, one single electrical layer. So, if you have a 8-layer board, you will have 8 such electrical layer masks, in addition to the solder mask, the legend print for the top and bottom sides. So, this is a very precision process, and this is, you can see it is a simple black and white contrast, but the black and white are of high contrast that provides better imaging once the process starts. So, all of these together is an activity called creating technology files. So, at the end of the routing process, you will create a set of technology files that will be sent to the manufacturer for doing all of these PCB fabrication processes. I hope this is well understood. In any project, whether it is a student project or a industry project or whether it is a research project, you have to do a lot of documentation. So, you can generate the following documents from your CAD software tool. You can create component list, you can create a list of all the components that are used. It is known as bill of materials, BOM, which indicates the component name, number of components used, cost of each component, total cost of components in the entire design, including vendor details and so on. In industry, BOM, bill of materials, is very essential to determine cost of manufacturing. Component layout printouts can be taken, PCB layout printouts documents can be generated. Test points. So, I was talking about bare board testing. In a particular board, there may be let us say 1000 nets, but there will be about 600 test points. So, these XY coordinates for your test points may be required for qualifying your board, and this data is fed to the flying probe tester, your automated equipment that can quickly give the shorts and open details. And as I said earlier, documentation for drilling, because drilling when you do a drilling process, there may be various vias that you are going to generate. Some are mounting holes, as I said, not necessarily to be plated, but these are plated to interconnect different layers, and in some cases there may be special cutouts that may be required for physically mounting your board onto the chassis of a product. All of these are done in the drilling process, and those details need to be documented, and the quality test procedures have to be followed. For any good industry that qualifies itself for high quality PCB fabrication, at every stage you have quality check, right after drilling, right after imaging and so on. So, we will see about that when we come to the fabrication process. When you come to test and evaluation, apart from the electrical test, another important test that people are doing today is the EMI qualification, electromagnetic interference. So, here you talk about or take care about reflections, crosstalk, noise reduction and so on. Okay. Then the other important thing is thermal. Thermal analysis can be separately done using the layout details of your CAD program. Here you can check the temperature profile of the board and you can find out hot spots on your board. What do you mean by hot spots? These spots are danger areas because of heat dissipation problems caused by poor layout of your board. Okay. If you are grouping 3 ICs together and all of them are going to dissipate, let us say 25 watts, okay, and that needs to be dissipated quickly, but you have not provided enough mechanism, then you have to take care to make sure that you separate these devices far away and also provide additional cooling mechanism. So, after your layout and placement, you will have to do a thermal analysis, and then if it is not okay, you have to do a component relayout till such time that your thermal analysis is okay. So, thermal dissipation issues are very important. Now, how do you take care of that? You can add a heat sink. What is a heat sink? Here I am going to show you a simple device which is a heat sink that can be mounted on top of a device. For example, here I have a printed circuit board and there is a active device here you can see. Suppose if this is dissipating a lot of heat, then I can mount it on top of the heat sink and try to remove the heat as quickly as possible before damaging the tracks and other structures. So, this is a heat sink material. In other cases, you can also use a fan. You can see here in this case a fan is used on top of a integrated circuit. Obviously, this material is lightweight, but it is positioned in such a way that it is mounted on top of the active device to remove heat. So, in your thermal analysis, you will have to carefully look at whether you require a heat sink or a forced cooling method like a fan, or you do not require these at all if it is not a major problem. So, this material of heat sink is a aluminum material and you can see this is lightweight and this is coated black, okay, and you can see the special corrugated structures here, and these structures are provided basically to provide more surface area, and more surface area means more heat can be removed from the active device. And for effective cooling, this is coated, this is black anodized aluminum, but black anodized. Okay. So, these are an entire set of technologies that are available today, which a designer should be aware of. Now, if you look at the slide, what is a net list? You must know how a net list is generated from your schematic capture. For example, if you take a net 1, if you look at any edit program, edit tool like a WordPad, if you load your net list, you will see these kind of listings. What does net 1 say? It connects op amp 3 pin number 2 to capacitor 4 number 4 pin number 1. From there the net goes to resistor 6 R6 pin 2, then it goes to R7 1, and that completes the net. So, this is net 1. So, net 2 again D1 1 to op amp 3 R7 C4. Like that you can have hundreds of nets, but you will see that typically in a net list the ground points is all grouped together. Okay. So, the ground connections are grouped together, and the reason is you can assign different track width. Okay. So, you can have a different thickness of copper for the ground plane to remove heat. Thickness of copper can be different. For these, the thickness of copper can be much less, because it is basically signal lines. Okay. So, in some cases you can use these as a heat sink copper, and therefore, you can have ground in different layers in a multi-layer board. So, you can interconnect with vias and push all these ground nets into a particular layer. So, this is the advantage of looking at a net list, and you can also edit them. Now, in the layout tool, as I mentioned earlier, there is the placement tool. Okay. You can do manual placement, you can do interactive placement, or you can do assisted placement, that is partially utilizing the expertise of the CAD algorithms that are there in the tool. So, you identify the components for auto placement, but the rest of it you can do manual. In the assisted part, you do some random or constructive placement to get started, and the rest of it can be done by automated placement. Now, you can do finally, if you are not interested in manual or assisted, then you can do automated, but experience always says that you have to better learn to do manual placement, because you know the circuit better, you have done the paperwork, and you know which component needs to go where and which component needs to be close to which device. Now, the reason for that is you have to make sure that you have minimum copper length for a particular net. You do not want too much copper added onto your board. Therefore, a good placement means a good attempt to place your components with minimum connection length. Okay. That should be the main goal, because your router also will look for minimum interconnection length. Then comes the next part of the tool called conductor routing. Fast results using CAD, right, and the ordering of routing when you start the routing program will be, it will first finish the shortest length and then go to the longest nets. You can also do pin and gate swapping if you give this command, or if you OK this particular process. That means, if you have different ICs or in a particular IC, if you have different pins with similar functionalities, IOs, during routing, if one of the pins is too far away, then you can allow it to swap to the next pin. Okay. So, instead of pin number 1, it can use pin number 8 to achieve a complete routing. Also, the gates can be swapped. Once the routing is done, it is going to take a long time if it is a very high dense board, and your CAD program is not going to do 100% routing. So, like you have done some manual placement, you also have to learn to do manual routing process for your interconnects. Okay. So, you should not depend entirely on the power of the tool to complete 100% routing. It is very difficult to get 100% auto routing. At least 10% will be incomplete, and you have to do manual. But in some cases, because of restrictions and because of electrical requirements, it is better that you do manual routing first and leave the rest of the simple traces to auto routing algorithm program. After the routing is done, you do what is known as a post route processing. What is that? When you talk about a double layer board, to connect layer 1 to layer 2, it will put a via and interconnect from top to bottom. But in this process, it will add a lot of vias during the first level pass, but you have to minimize the number of vias. Less vias, more reliable it is, because if you look at the manufacturing point of view, any via added can be a failure until and unless the process is foolproof. Okay. Therefore, try to minimize the number of vias. That is why we say optimize your routes once the routing is complete. Then you bevel the tracks. That means, you have a 45-degree track created by the CAD program, 90-degree, but then 90-degree is a unaccepted format for both electrical performance as well as for manufacturing purposes. So, typically you would like to create a 45-degree, take a 45-degree turn and provide these traces. So, the reason for moving from 90 to 45 is that a right angle corner is necessarily wider than the rest of the trace. This results in the decrease in Z naught, that is the intrinsic impedance of the trace, and therefore, it causes an impedance mismatch at the corner. Okay. When this happens, what happens is, when the signals are passing through, it causes reflections and creates electrical parasitic problems. There will be distortion in the signal and noise generated along the trace. And from the manufacturing point of view, if you look at a right angle like this, in processes like imaging and etching and so on, which you are going to see, this corner will be a major problem. This can chip off if the process control in processes like etching are not well maintained, and you also gain more area when you convert from 90 to 45, because if you want to run bus conductors like this for digital signals, you will get more area. So, convert your traces from 90 to 45, and the routers are grid based. So, before starting your routing process, set your grid distances. Okay. So, that can help in getting reliable completion. Now, this is a picture that I am giving you as an example of a finished layout by CAD. What are the things that you can see? And on the right you see the same design has been fabricated and assembled. So, fab plus assembly done here. Here is a mask, let us say, or a CAD view of a layout. You can see these are mounting holes, and you can see a lot of through hole components. For example, these are all through hole components. I write it as PTH, plated through hole. This is again a PTH. You can also see surface mount. This is a surface mount device. Okay, these are all through hole components. So, it is a mixture of through hole and surface mount device layout that you see here in this picture. The red and blue here indicates the traces on two different sides, which means for this process you will have to generate two masks. One will be as per the blue lines, the other will be as per the red conductor traces that you are seeing here. And red is much thicker because basically those are the ground planes that are generated, and the yellow traces that you see here is basically indicating the package outline. Okay. And these are legend prints which I talked about, and you can also see component names written here, which is legend print. Now, apart from the pad area and the through hole openings, all other areas will be covered with the solder mask. You can see in this picture the green color, this is the solder mask. Now, in this picture on the right you see the components have been assembled and completed. So, it is a mix of through hole and a surface mount device. Good optimization has been done to utilize the small area for a hybrid assembly of through hole and surface mount devices. Some of the components are very tall, you can see, like these display devices on the edge, some kind of a connectors at the edges, tall components here on the edge. So, repair and rework is easy. So, this is the kind of output that you get. Now, once you finish your CAD work, post processing, you have to optimize. As I mentioned before, what are the optimization operations that you can do in CAD? Now, creation of components and footprints through hole technology and surface mount technology. If you are working with a particular device which is not available in the tools library and which you are going to use it very often, you create a library of your own which can be utilized and which subscribes to the current existing standards, acceptable standards. Gate and pin swapping can be done. Manual, interactive and automatic routing can be done. Cleanup and optimizing the interconnection structure is a very must once you finish your first level pass of routing. In some cases, you may have to do at least 5 to 6 times the routing process by varying the layout, by changing a few components, achieving better interconnection, shorter lengths, and in terms of thermal also, and converting 90 to 45 corners and so on. So, the final operations will be, you can modify the segments manually, you can modify or change the track width later without going back to the schematic. So, metering and filleting the corner can be done. Copper maximizing, in some cases you want to pour copper in the inner layers, we call it as pour copper, because you are adding more copper to fill a certain area that can act as a heat sink, ground plane. Transfer between layers, you can move tracks from one layer to the other post processing. Then what are the post processing operations? You can create technology files, as I said, for sending it to the manufacturer. Now, For NC drilling machine, there is a universal format called Excelon. So, all CAD tools will usually generate an Excelon format file that will be used for NC drilling operation by the manufacturer. Then there is a universal format called Gerber for your photo plotting operation. The mask that I showed you has been generated by using a Gerber format. These masks are usually made from silver halide photofilms. So, if you focus once again on this mask, this is originally was a silver halide film. The black spots that you see here is basically metallic silver, actually oxide. So, the other areas where silver halide was present has been removed by a photo imaging process. So, essentially the starting material for this is a silver halide photofilm that you normally we used once upon a time in photography, but today most of us use digital cameras. Assembly drawing needs to be printed and documented, production planning document for manufacturing, and edit software will be used by the manufacturer for including. So, this is important because a manufacturer will look at your Gerber file, he will edit it and add tooling holes, he will add his logo, he will add batch numbers of manufacturing and so on. Okay. So, whenever you look at a board, at some corner you will see all these details of manufacturing, batch number or the company logo and so on, for easy identification of your design work much later. Now, we will come to looking at the wiring board configurations, because if you want to discuss more about CAD, you must now know what are the configurations that you have in the printed wiring board. The first thing is a single sided board. What does it mean? That it has copper on one side, this is the copper, and this is the core dielectric, okay, and this is the copper here that you see, and you can see that the other side there is no copper. So, typically in this case this is a single sided board. The assembly is done on one side, on the other side there is no assembly done. Okay. So, this is a single sided board. You can have a double sided board, which means you can have copper on both sides separated by a dielectric material. And in most cases you can also do assembly on both sides. For example, here you can see assembly has been done on both sides. Okay. Then you can have double sided board with layer interconnections using vias or plated through hole. If you look at this picture here, this is copper, okay, and this is also the inner layer copper. So, this is also copper, this is added copper, this is original copper. So, you have layers like 1, 2, 3 and 4 layers of copper, and this is the through hole, plated through hole. Where is the plating done? The plating is done here. This is the plated, and this is the start. This one is the starting copper. So, this is a 4 layer board separated by dielectric. So, this is a dielectric material, the green one that you see here, this is the dielectric material, and this is the, let us say, the solder mask that is protecting your via. You call it as a tent. Okay. So, this is a typical plated through hole double sided or multi layer interconnections. If it is a 2 layer, then you will have these 2 layers will not be there and you will have a double sided board. Typically now this is a 4 layer board. So, multi layer boards. Then you can have flexible and rigid flex board. As you can see in this picture, this entire board is flexible. I would now like to show you a flexible board. Here, as you can see, this is a rigid board. So, this is not flexible. The same circuit has been done on a flexible board. So, this is a flex board. Okay. Now, this is a rigid flex board, because as you can see this is flexible in the body and the ends, the edges are rigid. So, this is a rigid flex and a flexible board combinations are possible. Then we have high density printed wiring boards, where you can see micro vias are generated on the top of a structure like this, and that can be reproduced 3-4 times, one on the top, and the same thing can be reproduced at the bottom. So, this particular board which I am going to show you is a LAN adapter card PCMCA standard card. This is a 6-layer board containing flip chip, surface mount devices, and this uses micro vias for connecting those build up layers of the order of 90 microns or so. So, this is a high density board. Okay. So, these are the various configurations that you have for printed wiring boards. Now, the same thing is explained here in a different illustration to make you understand much better and more comfortable. So, you can see here this green layer is the dielectric, and here this is the copper that has been generated. So, this is a single sided configuration, and your signal, ground and supplies line will be on the top layer only. There is nothing at the bottom. Now, in this double sided configuration, what you see here, there is a copper here, there is also a copper here. You can have signal, ground and supplies at the top as well as at the bottom, and this is your dielectric material that separates the two conductor layers. So, the thickness of the dielectric is very important in determining the electrical performance. So, it can vary from 0.8 mm through to 3.2 mm. We will see about those things when we come to fabrication. And now, here what you see is a multi-layer board. You can see a basic core structure starting, and you can see the mask here that will be used to realize the copper traces. Then you have the pre-preg or the dielectric material that is added later. So, assuming this mask is now realized as copper layer, then you will have to build multi layers by adding a pre-preg, another set of copper layers, another set of dielectric, another core structure with 2 copper layers and so on. So, we will end up with 2 plus 2 plus 2, 6 layers of copper separated by 2 dielectric layers that have been added later, and these are the core dielectric materials. Okay. So, we will talk about these structures later, but think about the difficulties in creating electrical layers for each of these. So, we will continue with more on CAD utilization for various wiring board configurations in the next class.